All right, so introducing projectile motion. So the first question is probably, what is a projectile? No, that's not your first question? Well, I'm going to assume that it actually was. So projectile motion. Okay, so a projectile is any object that is, I guess, moving through space and is influenced by gravity. Okay, so what sorts of things could be projectiles? Well, let's write that definition down. Okay, so a mass moving through space that is affected by, I'm going to put only here, but that's sort of, it's kind of only the force of gravity. So things that would be considered projectiles. Yeah, a bullet would be. So if I threw a ball up in the air, the second that ball leaves my hand and it's flying through the air, it is a projectile. That ball will fall back down. Okay? Projectile. Let's say I have a cliff and I launch a ball off of it this way. Okay? It'll follow this kind of path to the ground. While it's in the air, it is a projectile. Okay? Now, one thing that we tend to do when we're talking about projectiles is we neglect to include air resistance. In real life, in the world, air resistance does play a role, although it's fairly minor in situations like this, but it does play a role. But in our physics learning here, we're going to do idealized projectiles, which means essentially we consider them to be traveling in vacuums. Okay? That just makes our math a little more manageable. And then there's one more type of projectile we'll specifically study, and that would be like a cannonball that gets kind of launched to the air. Or it could be like, you could say, it could be a football, or it could be like a bouquet of roses at a wedding. It follows this parabolic path through the air. Okay, and we're going to look at the mathematics of how all of this works. And to be honest, really, it's just an extension of kinematics. So all the formulas that we use here are just revamped kinematic formulas. Okay. So the first thing we need to remind ourselves of is acceleration due to gravity near the surface of Earth is 9.8 meters per second squared. All right. So in other words, in the y-plane, in all of these pictures, you have an acceleration that is aiming downward. Okay, and that affects how projectiles move and travel throughout the air. So we have seen type 1 projectile, which is either a dropped or tossed up object. Let's start with a question like this. A ball is thrown up with an initial velocity of, we'll say 15 meters per second. Find, and you've done questions like this before, find A, time to max height, B, time to return to the hand that tossed it, and C, final velocity. So this is going to be kind of like a bit of a review, seeing as how we've sort of talked about some of this stuff before. So if you imagine, here's someone's hand. This is going to look exactly like a hand. Doesn't that look like a hand? Oh, it's not bad. You'd know that was a hand. Yeah. So this hand has thrown a ball up in the air. And remember, we're going to neglect any air resistance. And so let's define a few things about this. The initial upward velocity is 15 meters per second. Okay? The other thing we know is that g is negative 9.81 meters per second squared. Or if you want, 9.81 meters per second squared down. Sometimes we stick the 1 in, sometimes we don't. It's sort of irrelevant. It's just personal preference, how much detail you want to put in here. Now, one thing to remember here, right, is at the beginning of this, gravity points in the opposite direction of velocity, right? Velocity's up, gravity's down. This means that the ball will slow, right? Seeing how its acceleration is opposite to its velocity. But eventually it reaches its max height, and at that point, its velocity has dropped to 0. Then, since gravity doesn't change, this object will start to accelerate back down towards the ground, right? And its velocity in the y direction will increase as it does so. So in that case, velocity and the acceleration are in the same direction, so that causes speeding up. So first things first, can we figure out the time to the max height? And the way I would do this is I would take your acceleration velocity time formula, which looked like this. And I would just simply rearrange it, where we would now say that time equals change in velocity over acceleration. And when it's at its, and we kind of do this in like, essentially always in 2 steps, but it does ask for max height anyway. So we know at its max height, its velocity will drop to 0. So what we have is we have 0 minus its initial velocity of 15 meters per second divided by 9.8 meters per second squared. And I don't know why I changed that to an A. It should still be a T, because that's what we're finding time. Oh yeah, and that's one more thing. We gotta make sure this stays as negative 9.8, or we'll get a negative value, and we know that you can't have negative time. So this is the time it would take for this ball to get to its max height, 1.53 seconds. Okay? Now I can tell you, but I want to show you too. The amount of time it took to go up is exactly the same as the amount of time it takes to come back down. But I think we're gonna want to show that to be true. So in order to prove that it takes 1.53 seconds to fall back down again, we're going to need to figure out first how high it went. Okay, so that's going to be the first job. So in order to do that, since we have an accelerating object, we need to do this. D equals VIT plus 1/2 AT squared. So we've got VI, which is 15 meters per second. We've got our time, 1.53 seconds. Plus 1/2 negative 9.8 meters per second squared times 1.53 seconds, and I can barely fit it, but squared. Okay, so this will tell us the total time, or sorry, the total height upwards that this object travels. So I get, my math gives me 11.5, roughly 11.5 meters. Okay, so that means that the ball has gone up 11.5 meters, and once it gets that high, its velocity equals 0. So now it's going to fall back down. So what we want to do is we want to try to prove that this also takes 1.53 seconds. Okay, so the up takes 1.53. We want to prove that the down takes 1.53. So how we're going to do this is we're going to look at our input data, right? Our input data is V0 equals 0. Right? Acceleration, or g if you want, negative 9.8 meters per second squared. I think I was just using, yeah, let's leave that one off of there. And our distance that it has to fall through, 11.5 meters. Okay, so we've got velocity, we've got g, we've got d. So, okay, so we're going to try to solve for time. And we'll go back to our formula that we've used, d equals vit plus 1/2 at squared. If you forget where these formulas came from, you can go back and double check in the kinematics section. Now, if we're talking about something falling from a height of 11.5 meters, okay, its delta d then is actually negative 11.5 meters, and that's sort of important, right? If you take this to be 11.5, to get back to 0, it's got to go negative 11.5 meters, okay? And g is negative there. So the initial velocity for something that's falling in this particular scenario is 0, okay? And we're going to rearrange this formula. So 2 times d divided by a with a root should be the rearrangement of this formula to solve for t. So what do we get? 2 times negative 11.5 meters divided by negative 9.8 meters per second squared, and we'll see what we get. So this will give you 1.53 seconds. Now, uh-oh, what is going on here? There. So now we see that there's a symmetry here, right? 1.53 seconds up, 1.53 seconds down. In the process of proving that, we found, actually we didn't find the height. Well, we did find the height, but that wasn't asked for. But now that we've sort of proven that, every time you do a problem like this, you don't necessarily have to repeat all of this work. It's okay to just say from now on that you know that the time on the way up is equal to the time on the way down. I won't expect you to prove that anymore. We've seen it, we've done work with it. Hopefully that's sunk in. The last thing it asks for is final velocity. So we should be able to get that. There's a few ways to do it. Probably the easiest way is just to go like this. Vf equals Vi plus At. Well, Vi is 0. So essentially we just have acceleration versus time. It's accelerating downward negative 9.8 meters per second squared for 1.53 seconds. And so this should be negative 15 meters per second. And hopefully we see that there's all kinds of symmetry all over the place, right? If it starts going up at 15 meters per second, it comes back down to the hand at negative 15 meters per second. The time going up, 1.53 seconds, is equal to the time coming back down, 1.53 seconds. This principle is true for this type of projectile motion, okay? There will always be a symmetry to these questions. Now, sometimes you might get a question, and this is later, where you're only dropping the ball, okay? Or even where you're only launching it off the side. Now you're really only solving the last half of this scenario, right? The part where it starts from 0 and falls some distance. So that's essentially our intro to projectile motion. In the next lesson, we'll learn about some of these other types, okay, of launched objects.